Welcome to another live session for the online astronomy class. Welcome. This will probably be our last session for the year. We'll start again in the new year. My university shuts down pretty hard for 2 weeks, and I'm off to India next week to attend a conference for the Dalai Lama where he's being presented with modern science. And my title in the talk that I'm supposed to give to him is, "What does the universe contain and where did it come from?" So that's going to be an interesting conversation. Meanwhile, the floor is open for your questions on anything to do with astronomy or Buddhism.
All right, the first question we have is from Irene, who sent this in via email. The question is, what kinds of information are gravity wave detections likely to give us that electromagnetic information can't provide? Is there any reason to start focusing on the building of gravity wave detectors?
Yeah, thanks, Irene. That's a good question because the gravity waves, of course, have just taken off as a new way of studying the universe. So the sort of short answer is that to learn about the universe, now that gravity waves are in play and we know how to detect them and we know there are phenomena to detect, we really need both. The problem and the limitation with gravity wave detection is that it's not very well localized in the sky, as opposed to a telescope or at any wavelength, which is localizing a source of radiation, within a small fraction of a degree. The error circles or error boxes, they're not really boxes, they're these sort of looping ellipses of positional uncertainty for the first 2 gravity wave detections, and for the marginal detection that was only 2.5 sigma, so they didn't claim it as a full detection. But for all those detections, the error ellipse or circle for the source is hundreds of square degrees. So that's just huge. And it doesn't localize it even to within the level of a single constellation. And that's, of course, because all you have is 2 different detectors. You have, and so the difference in the arrival time of the detectors and the different strength of the signal at the 2 detectors is the only constraint you have on the direction of the signal. And that's, of course, not good enough to say where the object was that went off. The distance in a gravity wave detection, because the 2 events that were seen last year were both over 1 billion light years away, that distance is measured not through any astronomical methodology, but it's basically the strength of the gravity waves. When you know from the signal the size of the black holes that were coalescing to provide that signal, the strength of the signal plus the way that gravity waves decline with distance from the source tells you how far away the merging black holes were. And so the distance comes that way, not in the normal way in astronomy from a redshift in an optical spectrum. So we really have very primitive and limited information on the gravity wave detection so far. And that's going to continue to be the case until there are new detectors in play. The prospects there are good. Of course, the detection of gravity waves kickstarted and gave a great boost to projects that were under development. The next big array to come online will be the Virgo array in Europe, which will have similar sensitivity to LIGO. And so they did, and then there's an Indian array, which is probably 2 years behind, and then one in Japan. So the addition of a 3rd array will start to localize the gravity wave signals that people anticipate detecting to something more like 10 or 15 square degrees. So it'll be 10 or 15 times better than it is now. The addition of a 4th array, either the Indian or the Japanese one, will start to bring it down to the level of maybe a square degree, something like the size of the full moon. And at that point, you really have a prospect of seeing what the source of the radiation was. So the issue, of course, is that you need both types of information, because just seeing the gravity waves doesn't tell you enough about the object under discussion. You really would want to detect it optically, or radio waves, or X-rays, or some electromagnetic form of radiation. And that didn't happen so far, and it's probably not going to happen for a few more years until the uncertainty in the position of the gravity waves comes down to a much lower level. But that will be needed to move this subject forward from its early pioneering phase.
All right, the next question is from an online viewer who's live with us. And the question is, there is a newfound asteroid that is a quasi-moon of Earth. What is a quasi-moon or a quasi-satellite? How many of them does the Earth have, and how did they form?
So I'm familiar with what you're talking about. And that's not a sort of standard astronomical designation, because a quasi-satellite or a quasi-moon, what does that mean? What it really means is that the orbit is not quite well enough to determine, to say whether the object is bound to the Earth and the Moon, the Earth-Moon system, in fact. And then that can happen because the orbital elements or information on most asteroids are actually quite poor. You have to observe them for many months, maybe even years, if they're moving slowly, to define their orbits precisely enough to know whether they might be fully bound to the Earth-Moon system. And that's the case in this situation. It's an object where the data is just not good enough to say if it's bound to us. But if it were bound to us, or nearly bound to us, it could have, for instance, a glancing trajectory where, based on its speed, there's some probability that as it passes near the Earth-Moon system, it becomes captured and goes into a bound orbit, a highly elliptical orbit. So that information is not good enough to determine that in this case. We do anticipate that there are going to be a number of objects that are very loosely bound to the Earth-Moon system. Things like asteroids that are on Earth-crossing trajectories, where they come close enough to the Earth to be deviated from their initial trajectory and essentially captured. And we expect there are such objects. They don't have to be close to the Earth. They could be 10 times as far away from the Earth as the Moon. And of course, they could be very small, tens of kilometers or even a few kilometers. And so they'd be very hard to find. So it's indeed possible that there are quasi-bound or quasi-captured objects around the Earth-Moon system that we don't know about.
The next question is from another live viewer. And the question is, what theory of the universe do you believe in? As in, what do you think is the nature of the universe, what it is, or what it's made of?
So the standard model of cosmology, which I pretty much adhere to, as well as most of my colleagues, because it has a lot of evidence to support it, is of course the hot Big Bang. And that is based on a triumvirate of core evidence, one of which is the expansion of the universe measured by the redshift, discovered by Hubble in the early 1920s. So we have the expansion of the universe, the fact that galaxies are all receding from one another, which indicates expanding space-time, and that expanding space-time is understood in terms of general relativity. Then there's the detection of the microwave background radiation, discovered in 1964, which matches the temperature, just under 3 Kelvin, predicted for leftover radiation from a hot Big Bang that happened 13.8 billion years ago. And the third piece of evidence, not as familiar to most people, is the fact that the universe contains about a quarter helium by mass, with most of the rest hydrogen. And that amount of helium is too much to be explained by stellar nucleosynthesis in all the stars in the universe over 13.8 billion years. So it must have come from somewhere else in some other way. And the Big Bang model correctly predicts the amount of helium we see in the universe that cannot have been created in normal stars. So those are the pieces of evidence that make the hot Big Bang model the current theory of the universe. But there's some big uncertainties. The uncertainties over what are the dark matter and dark energy, which together form about 95 to 96% of the contents of the universe. So we really don't know what most of the universe is made of. There's also the question of what caused the Big Bang, which is beyond the theory. It's not part of the model to say what caused this expansion from an infinitely hot, dense, early state. And there's also the question of whether there's something beyond the bounds of the visible universe. So we have a model that explains the galaxies we can see, and we think it's likely that there are regions of space and time that we cannot access with our telescopes and our observations. But the theory doesn't really say much about those, how vast they might be, how much of a subset of overall space-time our observable universe is. So that's quite a lot of uncertainty, but none of it goes against the idea of a hot Big Bang as the basic explanation for most of modern astronomy data.
So the next question from a live viewer is, how will the future of astronomy shape science fiction?
Well, that's a fun question, because I mean, I don't read as much science fiction as I used to, or I have at some stages, but I still read some. And the coupling between science and science fiction is obviously very, very close. And it's healthy that it's close. Science fiction spans a range. Of course, it ranges into social areas of which don't tie so closely to the science, and then the hard science fiction, which is very much based on the laws of physics and not wanting to violate those, where speculation is kept to a minimum. So the influence of science on science fiction is really strong now, and it's particularly strong because of cosmology, because of the nature of the universe we live in and the profound questions that we're able to answer and some that are still unanswered, which leaves an opening for science fiction. And because of astrobiology, the search for life in the universe, where again, we know a lot more than we did a decade ago. The incidence of Earth-like planets, for example, the abundance of the ingredients for life in various locations, but we still have no idea if life happened anywhere else or it was just a fluke on the Earth. And once again, that leaves an enormous opening for speculative writing and science fiction about what the nature of biology elsewhere in the universe might be. So this is a very good time to be a science fiction writer, because you can tether your science fiction in science without being a total hard science fiction writer. And yet that science is not so well defined that it doesn't give you enormous creative latitude in writing a great story.
All right, the next question is from a live viewer, and it's about resolution. You mentioned that the human eye has a resolution of 60 arcseconds, and Hubble has a resolution of 0.05 seconds of arc. Does this mean that the human eye can distinguish 2 points separated by 1 minute of arc? Can you explain what that notation means?
So resolution in this term means angular resolution, and indeed it's a figure of merit. It's a major figure of merit of astronomical observing, and it's essentially driven by optics. So the angular resolution of any optical device, whether it's a telescope or a microscope or an eye, human eye, is proportional to the inversely proportional to the size of the aperture of the light gathering device. So the bigger the aperture, the smaller the angular resolution, which means the finer the angular resolution, and it's also proportional to the wavelength. So longer wavelengths, larger wavelengths correspond to bigger or poorer angular resolution. So images are sharper, for example, in blue light than they are in red light with the same optical detector. So the eye, of course, is a small device. So the angular resolution, just using the same formula that you would use for a big telescope, is based on the pupil, the open eye. And of course, at night, the pupil is more dilated than in daylight. And so you measure the size of the pupil at night. And that number, which is less than a centimeter, will give you what the angular resolution of a human eye is. Now, of course, there's variation from individuals. There's also variation in the depth that humans can observe. There have been articles written in Sky and Telescope, I think, and Astronomy magazines about how much deeper certain people can see in the night sky, on the same night sky, than other people. It's a factor of 2 or 3 difference, actually. And that's not because of age or degrading of the eye. It's just that eyes are built differently, and some are better than others. But in terms of angular resolution, that's more pure optics. And so human eyes actually do have a resolution. It's actually a little more than 1 arc minute. It's sort of in the range of 2 to 3 arc minutes. So what is an arc minute? An arc minute is a 60th of a degree, and the moon, for reference, is 30 arc minutes across. So the angular resolution of the eye is about a 30th, or maybe a little less, or 20th of the moon's angular size. And that means if 2 objects, 2 point sources of light in the sky, were separated by closer than that angle, the eye would not see them as separate points. They blur together to look like 1 point of light. So it affects the ability to resolve closely separated objects. If instead you're looking at a surface like the surface of the moon, it affects the minimum size of a crater or feature you could see, because it's the amount of blurring that's inevitable due to your optics. And of course, it also affects depth, because as objects bleed together, you stop seeing them individually, and so it limits the depth you can see out into space.
All right, the next question is from somebody who is on with us live. And they ask, what observational research project would you suggest to an amateur to conduct with a regular home telescope?
So interesting question, because amateur astronomers' telescopes have improved over time. There have been sort of 2 waves of this, or 2 aspects of this. One is the spread of what are called go-to telescopes, which are small telescopes from the classic manufacturers like Celestron and Meade, of various optical designs, where they're controlled, their equatorial mounts are controlled by motors and GPS and sensors, so that you no longer have to know your way around the sky. You essentially just tap in to the telescope or to the control panel the object you want to see. It has those in memory. It knows where it's pointing, because you calibrate these telescopes by pointing at Polaris typically, and it will go automatically around the sky to various objects. So that takes a lot of the pain, also takes away some of the knowledge required to do observing. So, but that will not help you do research. These are typically pretty small telescopes just used for sort of deep sky things like looking at Andromeda Galaxy or the Orion Nebula or star clusters. At another part of the subject, of course, is used more and more sophisticated CCDs, or charge coupled devices, where the eye is not the detector. CCDs, which are used by professional astronomers and cooled with liquid nitrogen to have very low backgrounds for very deep observations, can be used by amateur astronomers, where they might, for instance, be cooled by a photoelectric cooler rather than liquid nitrogen, and that makes them actually quite cheap. They're down to a few $100s sometimes. So you can get a digital imager to put behind your small telescope, or maybe a telescope up to 10, 15, possibly 20 inches collecting diameter, and you will be seeing quite deep, certainly deep enough to do research, astronomy research. And then the question becomes, what's the best project? The best way to get started in this is to join one of the networks of amateur astronomers. The most venerable one is the Amateur Variable Star Observer organization nationally, because amateur astronomers have been usefully observing variable stars, many of which are bright enough to observe with small telescopes, where what really is required is patience and the ability to observe them night after night, month after month, year after year. Astronomers have been doing that for over a century, since well before there were CCDs. But with CCDs, you have other possibilities. You can survey nearby bright galaxies to look for supernovae. That also requires a cadence of observation where you go back night after night, or maybe every few nights and every few weeks, to look for the occasional detonation of a massive star, which will show up as a bright spot in the arms of the galaxy typically. In some specialized cases, amateur astronomers are even able to do exoplanet work. Some of the transiting exoplanets can be observed with fairly small telescopes of 10 inches or smaller. And again, there are networks that are being set up to help amateur astronomers do this. I don't off the top of my head know the URLs of these groups, but both in all those three areas I mentioned, in variable stars, in exoplanets, and in supernova hunting, amateur astronomers are making substantial contributions, because what they bring to the table is pretty good hardware, dedication, and a lot of time to do devoted to observations. Professional astronomers tend to get their time on big telescopes in very small chunks, a few nights at a time, or a handful of nights a year scattered around the year. And so there's some types of science they can't do very well, where amateur astronomers can make a real contribution.
All right, the next question is from a live viewer who asks, regarding your visit to India, what is the Buddhist view of Earth and orbiting the sun? I guess you could expand that to be, what is the Buddhist view of the universe?
Sure. So Buddhism isn't monolithic in its views of science or of cosmology. I've experienced variations in those views. So generally, Buddhism is an offshoot, if you like, of Hinduism. The Hindu tradition goes back 4,000 or 5,000 years in Asia, and mostly in India. And the Buddhist tradition is relatively young in the sense of only going back 1.5 millennia instead of 4 millennia. But Buddhism shares many common elements with Hinduism. In the cosmology of Buddhism, which again emerged from the beginnings of the subject, the time of the supposed historical figure of the Buddha, there was a classical tradition of cosmology where Mount Meru, a mountain, a sacred mountain if you like, is the center of the universe, and the Earth are right around it, and then the dome of heaven, the celestial vault, is arranged above it. This is a sort of geocentric view of the universe, which doesn't really accommodate modern astronomical knowledge. It's a picture, if you made an image of it, that's very similar to pre-Copernican views in Europe, the kind of views you might see in sort of Roman times or medieval times in Europe. But modern Buddhists, and even for the last 100 years or so, Buddhists have moved away from this historical tradition based on Mount Meru, the story of Mount Meru. And so the monks that I teach, for instance, every year, have been brought up with a knowledge that the universe is a large place, that the Earth is not the center. They're fully aware of the Copernican revolution. They're fully aware that the universe is a large place where our star system is not the only one, and our galaxy is not the only one. However, they do tend to have slightly sketchy views of what the universe consists of and how large it is, unless they've been formally trained. But that's true, I would say, of anyone, not just of Buddhists. So in my experience, Buddhists in their religious tradition are completely comfortable with the idea of the universe as a vast, possibly infinite place. They're completely comfortable with enormous spans of time, with the universe being 13.8 billion years old, for example. They're also comfortable with life being fairly widespread in the universe. There's no insistence in Buddhism that the life on Earth or humans, while they may be special in terms of living organisms, there's no sense that they need to be or must be unique. So my experience of teaching Buddhist monks is that they're if not familiar with the elements of modern cosmology and astrobiology, their tradition allows them to be very comfortable with modern scientific knowledge.
All right, the next question from a live viewer is, what is the size of a comet and how could they bring water to the Earth?
So the comet core is a few kilometers, maybe 5 to 10 kilometers. So they're fairly small objects. Remember, the largest asteroid series is about 1,000 kilometers across. So comets are hundreds of times smaller than the largest asteroid, and dozens or tens of times smaller than a typical asteroid, which means they're, fractions of a percent of the mass. So they're very small, rocky, icy bodies. And going back to the model of the sort of the dirty snowball model of Fred Whipple in the 1950s, there is a sense that that's still a fairly accurate description. The comets are a combination of icy and rocky material. And because the gravity is weak, because they're so small, that is often very loosely aggregated. And so we've seen examples, as with Shoemaker-Levy, the comet that plunged into Jupiter in 1995 and was ripped apart by tidal forces on the way in. The comets don't have a lot of structural integrity because of what they're made of and because their gravity is weak. And so that's still a fairly legitimate view of comets. How they could bring water to the Earth, there's still an active debate over where the Earth's water came from. And there's no unanimity on that. And the reason for the lack of unanimity is that although it was an early idea, a strong idea, that indeed comets were the water delivery mechanism for the early Earth, where in the early solar system, there's a lot of debris left over from formation, comets and asteroids, of course, ending up in the inner solar system, slamming into the Earth at frequencies hundreds or thousands of times higher than today in the first 100 million years of the Earth's formation, would have brought with them their icy material, which of course then becomes the Earth's oceans. The reason the story doesn't completely hang together is because of what's called the deuterated fraction in these comets. So normal water has a small fractional component of deuterated water, which is to say, instead of the normal hydrogen atom bound to an oxygen atom, you have deuterium. So there's a neutron as well as the proton. That's what deuterium is. And that means, of course, it's heavier. It's called heavy water. So you can measure the deuterium fraction in the Earth's oceans. And because we've sampled two, and with indirect information, a couple more comets, we can ask what the deuterium fraction in them is. And only, I think, in one of the cases is it close to the Earth's oceans. In the other cases, it's quite different. So the story doesn't completely hang together now based on the small number of comets we've sampled. So we're being left to ask, where did the water come from otherwise? There are various other theories, one of which is that the Earth was always there, that the Earth was built into the formation and existed in the deep mantle and was sort of gradually extruded out through pressure and heat towards the surface where it became the oceans. Remember that the oceans of the Earth are a really small fraction of the mass of the Earth itself. So the theory that had comets putting it there is called the late veneer theory, because the oceans amount to just a thin dusting of liquid on the surface of what's a generally rocky planet. But it's an open research question as to where the oceans of the Earth, or by extension any other terrestrial planet among all the Earths we're finding now and other star systems, where those oceans came from.
All right, our next question is from a live viewer who asks, is there a way to know about objects beyond the observable universe?
In principle, there is, and it sort of involves patience at some level. Objects beyond the observable universe are, of course, hypothetical, because if we don't have information or data on them, then we're relying on a model for the fact they exist. So just to back up, the basis for believing that there are objects beyond the observable universe is the fact that in the early parts of the expansion of the universe, any 2 points in space were moving apart faster than the speed of light. The universe, for the first 2/3 of its existence, was decelerating in its expansion rate. In the last third, it started to accelerate again due to dark energy. But that means that there were parts of the early universe where those parts were moving away from each other faster than light speed, and now they are unavailable for us to observe because there's no way for light to have reached us in the age of the universe. So one way to get around this, of course, is just to wait long enough. We can only see objects where light has been able to reach us given 13.8 billion years of light travel time. So obviously, as we wait longer and longer, we're going to see yet more distant regions. So that's one answer to the question, just wait. But that's a very slow and inefficient way of seeing previously unobservable regions, because the universe is so big and our lives are too short. And but unfortunately, that's where we're stuck right now, because all we can do is say the model predicts as yet unobserved regions of the universe, and there's nothing we can really do to access them. The other thing that's going on, of course, is the acceleration. And that means that we're actually losing parts of the universe that we had already seen. So there are parts of the distant universe where the objects may have receded beyond view and then were brought back into our view by the deceleration, that will subsequently, in the future, be taken away from our view again by the accelerating expansion. So it's a very strange idea, the fact that there are distant galaxies or regions of the universe that once could have been seen, were then removed from view, and then came back into view again. So this is the strangeness of modern cosmology.
All right, the next question is, do you think that there are more electromagnetic waves that we just can't detect with shorter wavelengths than gamma or longer than radio waves?
There's no limit in physics on the wavelength or energy or frequency of electromagnetic waves. Those 3 quantities, of course, are interrelated. It's a question of whether nature makes them. So let's start at the low end, the low energy end, the long wavelength end of radio waves. The longest radio waves that we have the technology to sense or detect are something like 10 or 20 meters long. Those really long radio waves. We can't actually detect those radio waves from the cosmos because they bounce so efficiently off the upper atmosphere, which has some magnetized components, so it sort of reflects long wavelength waves, that they're essentially trapped. So they don't get in and they don't get out. But we can create those waves with radio technology. There's no particular limit on the length of a radio wave you can create, but at some point you need enormous antenna arrays to even detect it. And also there's an issue of the energy. At some point the energy of those waves starts to get so low that other noise sources, just natural noise sources, will sort of stop you from being able to detect it. So the practical limit at the low end is based on extremely low energy and also developing a physical device large enough to create or sense such a long wave. At the high energy end, again, there's no limit in principle. The highest energy electromagnetic waves that we routinely deal with are, of course, high energy gamma rays. Those do not also reach us from space because the Earth's atmosphere is opaque to them. So those are detected by gamma ray telescopes in space. NASA has one, and the Europeans have one at the moment, I think. Those could even extend to extremely high energies, and we think such high energy waves are produced, for example, in the vicinity of black holes. Black holes are extremely efficient particle accelerators, and those accelerating particles will produce extremely high energy radiation that's proportional to the energy of the particles that are being accelerated. So nature, we think, is able to make gamma rays of energies thousands or even millions of times higher than anything we've detected so far with our telescopes, but we don't have the means to detect those either.
All right, our next live question is, how do you think the new administration in the US will affect NASA and government spending on space research?
It's an interesting question of how science will fare in the new administration in the US, and scientists, of course, are watching and waiting anxiously for how science will be affected. I'm not going to venture into political waters, except to say briefly that the scientists who are the most concerned are clearly climate scientists, because we have an incoming upper administration that's pretty much stacked with people who think climate change is either a hoax or didn't happen or isn't happening. And so they're swimming against the tide of 99% of climate scientists. In space science, it's less clear what the situation is going to be. NASA and the National Science Foundation, the two main federal funding agencies for astronomy and space science, have enjoyed historically bipartisan support from both sides of Congress and from both parties for decades. And it's really unlikely that that will change under this administration. So most space scientists and astronomers are mildly optimistic, or at least not very anxious, that funding will tank or there'll be some major hit to the budget. But it's also not clear what the commitment to large new programs will be, because this is an administration that has also staked a claim towards government being smaller, trimming government spending, especially non-discretionary government spending. So there's already an indication in the next administration that the part of the budget that's outside of entitlements and outside the military, which is now a small fraction of the budget, but it includes all the agencies like NIH, NSF, and NASA, will start shrinking at maybe 1% a year. Even that level of shrinkage will be painful for all the people trying to do science in this country. So there's no great optimism that there'll be a new injection of resources. I think the best most scientists are hoping for in my field is just holding the line and steady budgets in the next few years.
All right, our next question is, are we sufficiently aware of objects that cross the Earth's orbit? Could we anticipate an impact similar to the one that occurred 60 million years ago?
So very important question, of course. Can we anticipate, head off, and even diagnose a potential impact? And the short answer is mostly yes. Mostly yes, we can anticipate, detect, and even with technology, head off a potential impactor. The practical problem, of course, is that the impactor could come from any direction. However, we think that most of the impactors are likely to be scattered. They're likely to be asteroids that are scattered or deflected or collide and move out of the asteroid belt into Earth-crossing orbits. And that, of course, means that they will occupy the ecliptic or some strip of sky that's fairly well defined. And so people looking for such Earth-crossing objects have a fairly small piece of real estate on the sky to look at. And the surveys for those, sponsored by NASA, because the US Congress instructed NASA some 15 or 20 years ago to find all the potential Earth-devastating objects out there. NASA declares that it's 90 to 95% complete on that task. But there's a big caveat. The caveat, of course, is that 95% is not 100%, and so they're not done with it, and there's some objects of the size of maybe a few hundred meters that may have escaped their attention. And the other caveat is that for objects that approach the Earth from a direction well away from the ecliptic, outside the plane of the solar system, are much harder to detect because you need to survey essentially the whole sky to find them. And that's really hard and difficult to do for small objects that might, at the moment, be far away but coming closer. And surveys are underway to try and do that, but it's going to take actually years for those to be complete. So mostly we're fairly secure on this, down to the level of a few hundred meters. Now, a few hundred meters is an interesting size because the asteroid killer was a much bigger object. That's a catastrophic, biosphere sterilizing, Earth destroying, catastrophic impact. Something a few hundred meters traveling at typically 50, 60,000 miles an hour relative to the Earth, that's going to take out a continent or a big chunk of a continent. It might not necessarily cause global catastrophe. So we're probably safe from the true civilization destroying objects, or we'll know about them. But for things that could cause a regional catastrophe and a huge problem for the planet, it's very hard to be complete, and we're not complete in our protection, in our diagnosis of their existence.
All right, the next question is, do astronomers ever look at the Quran for astronomy projects? And they're particularly intrigued by the idea of rolling back skies at the end and wormholes for transportation.
So I'm not a scholar of the Quran at all, but I have met scholars of the Quran, and I've met astronomers who have studied the Quran. And I've read a few short articles at meetings I've been to. The role of astronomy in Islam and in the sacred documents like the Quran is interesting, because the Quran, of course, contains an admonition or an advisory, an instruction basically, to not make it's based on a idolatry idea, which is present in other world religions too, to not represent models or physical descriptions or representations of astronomical objects. So illustrations in the Quran essentially never contain images of things or pictures of things or maps of the sky or the way the sky looks. However, the Quran does contain descriptions of astronomical events. Mathematics was a strong part of the Islamic culture, and in fact, mathematics did extremely well in that part of history on the Earth. So there are mathematical derivations and mathematical descriptions, but not physical descriptions or representations. So it's a kind of an interesting situation.
All right, the next question is, recently some scientists presented a new model of our universe in which they describe it as having a cycle of 4 different phases of expansion and contraction, and our current universe is in one of these phases. Have you heard of this, and can you expand on it?
There's one theory, there may be more than one. The one I'm familiar with, because it's been around for a while, is called the ekpyrotic theory of cosmology. That's from a Greek word for rebirth out of fire. And that model, which came from theorists, I think, at Princeton and the University of Cambridge, is a sort of cyclic universe model. It actually holds that the Big Bang was not the origin of everything forever, but was part of an episodic series of events. And the context for this episodic series of events is higher dimensions of space-time. It's a sort of a brain model of the universe, where brain is short for membrane. Membranes are dimensional objects that are embedded in a higher dimension, such as our universe, a 3-dimensional object, being embedded in 4-dimensional or 5-dimensional superspace, if you like. So this ekpyrotic theory is based on membranes or brains, and it holds that the expanding universe and the Big Bang was a collision of 2 3-dimensional brains in a higher space that may involve 4, 5, or 6 dimensions, depending on the underlying theory in mathematics. And in this theory, there's tension between the brains, or tension in a physics sense, such that the brains can come together, collide, and then repeat that cycle on long time scales, like trillions of years. And so in that sense, you can have an oscillating or cyclic universe, if you like, where there's a Big Bang, and eventually a contraction, and eventually an expansion again. There's sort of like the bouncing universe idea back from the 1950s, which was sort of discredited. So this is bringing back that idea into the modern context, basically of string theory in higher dimensions. So it's very speculative, but that's the question you're alluding to is a legitimate theory that tries to go beyond the Big Bang to say why the Big Bang happened, what's beyond the Big Bang, and is there a history of the universe before the Big Bang? And the answers to those would be yes in this theory. As for support of that theory, it's going to be hard to find, because that's going to require some evidence somehow imprinting into our universe of these previous cycles. And of course, that will require us to access these higher hidden dimensions, which we simply don't know how to do yet.
All right, the next question is, today we can observe gravitational waves from very big events such as big black holes colliding. What can we hope to observe with gravitational wave detectors in the future as the technology matures? And then sort of follow-up or related question is, why aren't we seeing black hole mergers constantly?
Right. So I mean, I'll answer the second part first. Why have we only seen a couple of events? You know, the last LIGO run. You'll also be aware that LIGO recently underwent renovation, improvement of its detectors, lowering of its noise sources. So LIGO just started fairly recently on a new run, which should give it somewhat higher sensitivity than it had before. So given that it detected 2 solid and 1 possible event in its last science run, we can anticipate more science events, maybe as many as 6 or 8 in the next run starting now. That's very exciting. But why didn't it see more? And the answer is simply sensitivity. The reach of LIGO depends on its sensitivity. The intensity, because LIGO is detecting the amplitude of a space-time distortion rather than the intensity of a light wave, as a telescope would do, the strength of the gravity wave goes down as the distance. So if you can improve the sensitivity by a factor of 3 of a gravity wave detector, you can see events that are 3 times weaker, or the same event 3 times further away. Well, 3 times further away goes as the cube, has 27 times more volume. So improving the sensitivity by a factor of 3 gives you almost 30 times as many events. And that's the situation that LIGO's in. That's what people are working towards. A situation where instead of seeing a couple of events a year, you improve that factor of 30 in the very next phase of advanced LIGO after this year, and suddenly you start seeing an event every week or more often than that. So it's purely a matter of sensitivity. Having detected these events, astronomers know what the density of black holes and binary black holes is in the galaxy and in other galaxies. So we know the events are out there to be seen. It's just a matter of sensitivity. And as for other types of events beyond coalescing black holes, LIGO, or advanced LIGO in its next iteration, when its noise is lowered, should start to see other events. For example, any asymmetric stellar cataclysm will generate gravity waves, and that includes supernovae. So supernovae, we know, are happening all the time. And when the supernova is asymmetric, and there are various reasons that might be the case, a supernova will release gravity waves. So we can start to anticipate seeing supernova events. If we have more sensitivity, we can also expect to see neutron star coalescences. So in terms of increasing gravity wave strength for compact objects, stellar remnants, you have neutron star coalescences, you have a neutron star combining with a black hole, and then you have 2 black holes. There are more, because they're based on lower mass stellar remnants, there are proportionally more neutron stars than black holes, maybe 5 or 10 times as many. So when you get the sensitivity to see neutron stars coalescing, or a neutron star coalescing with a black hole, you're probably going to be looking at 10 times more events than just when you can look at black holes coalescing. So that's another way improving sensitivity will bring in another set of detections. The final sort of wild frontier of gravity waves is what happened in the Big Bang. Big Bang was obviously a situation of intense gravity, where the gravity force was changing rapidly, and that's the primary condition for gravity waves. So every Big Bang model of the early universe predicts there will be some gravity wave signature of the Big Bang very early on. Unfortunately, that signature is likely to be very stochastic, which is to say random variations in strength, and it'll be all around us. It's coming from the universe itself, so the signal will come in all directions. So it's going to look very much like a noise source to an instrument like LIGO. And that's a little frustrating to the physicists, because that signature of the Big Bang is the very hardest thing for an instrument like LIGO to detect. And nobody's really confident that LIGO or its successors will be able to see gravity waves from the Big Bang.
All right, the next question is live, and it is, how real is the idea of quark stars?
It's a speculation that the stellar astrophysicists I've talked to think is a legitimate speculation. So the background to this is that quarks are, of course, the subcomponents of nucleons, or protons and neutrons. Each neutron, each proton consists of 3 quarks, various combinations of these fractionally charged particles. And the nature of the strong force that binds a nucleus, an atomic nucleus, together is that strong force has a strange way of behaving, which stops the quarks from being liberated. So basically, as a quark tries to leave a nucleus or move apart from another quark inside a proton or a neutron, the tension of the force between the quarks increases, which means they are bound. So they're very strongly bound, and free quarks are not routinely observed. With great difficulty in high-energy accelerators like the Large Hadron Collider, there has been indirect evidence of quarks. Nobody's ever seen quarks released into the wild, if you like, out into the world. But what people have seen is quark jets, where if you put enough energy into a collision, you can liberate the quarks for very tiny fractions of a second. And that, of course, helps to show that the quarks exist. Now, what is speculated is that in some massive stars, where the material is already at the density of nuclear material, which is to say a neutron star or a black hole. If it was a black hole, of course, you can't see what's going on. Neutron stars, at least we know how to study, because they're electrically neutral, there's no event horizon, and so in principle, there's information that can reach us from a neutron star. And in some theories of this nuclear matter, which is essentially atomic nuclear matter, there are situations where the quarks will interact with each other. Essentially, they will cooperatively interact and sort of form almost a quasi-fluid of quarks in the neutron star. And that will have signatures that potentially could be observed from the Earth. So when people talk about quark star, they're just talking about the fact that a neutron star is essentially a sea of quarks interacting with each other at nuclear matter densities. And those quark interplays and interactions could lead to observable effects. None have yet been observed, however.
All right, our next question is, are you familiar with the company Slooh, S-L-O-O-H? What do you think of Slooh and their business model, and do you think more companies will crowdsource telescopes?
So this one I have to pass on because I'm not familiar with. I don't even think I've heard of it.
It's like an online robotic telescope network, apparently.
Right.
All right. So the next question is, what is your opinion of the astronomy content in Wikipedia?
Yeah, that's a good question, because I'll bring it right to currency, because our professional society, the American Astronomical Society, had just had an initiative this year to sort of crowdsource astronomy expertise, primarily graduate students or advanced undergrads, to try and edit Wikipedia articles and make them better, or smooth out the problems. Either build articles that didn't exist, or make existing articles better, or correct errors that they found in the core articles. So that's a matter of going with the flow. Academics and people even in my discipline are very mixed on Wikipedia. Some people don't like the fact that it's not as authoritative as a refereed article or a textbook, where there's some editorial control and where an avowed expert is responsible. Wikipedia editors can almost be anonymous. And of course, you're crowdsourcing it, so an astronomy article could have many hands involved in it. All I can say is we did a little experiment in my work group a couple of years ago, where I had the students in the group, the astronomy students, inspect a few hundred Wikipedia articles on astronomy and really look hard for mistakes. And they were very hard to find. I think in nearly 200 astronomy articles, there were 2 significant or substantial errors and about 15 or 20 minor errors. That's actually a pretty low error rate, and some real encyclopedias might have a similar error rate. So in astronomy, it appears that the accuracy is pretty good, and I think we can understand that because these are technical subjects. So if you're talking about an article on stellar nucleosynthesis, it is really, you essentially can't write an article like that at all if you're a total amateur or not familiar with the subject. So these articles do tend to be written by graduate level people. In fact, many of the Wikipedia articles in astronomy and astrophysics are actually almost too technical for their purpose of reaching a broader audience. So I've seen articles on astrophysical topics which I think are written essentially at the graduate level with a lot of math and a lot of derivations and equations, and the average person running into them would not know what to make of them at all. So if anything, rather than being dumbed down or erroneous, some of the Wikipedia articles in my subject are actually too arcane or too technical or too difficult. So I think the philosophy of accepting Wikipedia as a one-stop shop for information, which it is for most people, and especially most young people, on science or on anything, and just try and make it better. Because anyone who has expertise in a subject can be a Wikipedia editor, and they've been saying for now a few years that the concern in the Wikipedia community is that the number of editors is actually shrinking, and that's an unhealthy situation. So having more editors in the gene pool with content expertise in any subject, including astronomy, is a good thing. So I would encourage graduate students or advanced undergraduates especially to sort of take that on as a thing they might want to do.
All right, we seem to be having a little glitch in the live stream, but we're going to answer one last question, and I believe it's still recording, so people can watch it after the fact. But the question that we'll address is, what do you think of the Fermi paradox? Is it a real thing?
So the Fermi paradox is framed by this, and it's sometimes called the Fermi question because it's sometimes framed as the question, where are they? And it's based on Fermi's 1950 speculation that the universe should have a lot of intelligent life because there are many sites for life and a long time for it to have evolved, and that some fraction of those life forms should have gained the capability to leave their planet and explore or travel through the universe or the galaxy, and so we should see evidence of their existence. And since we don't, because Fermi didn't believe in UFOs as evidence of alien visitations, the question becomes, where are they? It's not correctly called a paradox. Philosophers have, corrected me when I've occasionally used this in talks. This is not a paradox. Is an internally contradictory set of statements, and the Fermi question, if you like to call it by what I prefer to make its name, is not technically a paradox, because you'd have to have a reason to believe that intelligent communicating life actually exists and for some reason has chosen not to communicate for it to be a paradox. It's an interesting question, and my simple answer would just be that astrobiology is a subject and our exploration of life in the universe is at too primitive and early a stage for us to even approach the answer to the question, where are they? We have not even found all the places where there is life on the Earth, microbial life, not advanced life. I think we found all of that. So it is easy to have life in the universe, even in the nearby universe, that would escape our detection. And once you have advanced technology and the ability to have a very low footprint in the universe or be invisible or shield or cloak yourself, then it's also very easy for intelligent life or civilizations to exist without us knowing about it. So I think the premise that if they were there, we'd know about it is simply not correct. It's not supported by evidence. And so I put the Fermi question in this intriguing category where it's certainly fun to talk about and speculate, but we do not have the tools to answer it yet. Thanks very much, and we'll be back with you in 2017. Bye.